Good morning, everyone. So today let us look at transistor characteristics. Okay. So what we will do is, as you know that there are three types of transistor characteristics: common base, common emitter, and common collector. Okay. So objective of this experiment is to plot the transistor characteristics and obtain the H parameters. Okay. So we will do transistor characteristics for common emitter mode, and from the common emitter characteristics we can find later on the H parameters. Alright, so once you know the H parameters of common emitter configuration, you can use the conversion equations to find the H parameters of common base and common collector. Alright, so let us look into the connection diagram. So this is the input power supply and this is the output power supply. Input power supply is rated for 0 to 5 volts DC, and output power supply is rated for 0 to 12 DC. Okay. So these are the terminals provided for the external connection. Okay. All right. So the transistor is placed in the slot provided, base, collector, and emitter. Alright, so the positive terminal of the power supply is connected to the current limiting resistor. So the point is over here. Alright. So what we have to do is we have to just connect the opened circuit. Okay, over here there is an open circuit. This we are supposed to connect. So, and then you have the terminal flow for microammeter, right? The positive terminal of microammeter, that is here. Okay, that you are going to connect to positive of the digital ammeter. Okay, that's here. And the negative terminal of the ammeter is connected to the negative terminal of the digital ammeter. Okay. And on the lower side you have an open circuit between point Q and point Q D. So just short it with a wire so that there will be continuity. And on the output side you will find a milliammeter, right? The negative terminal is connected to the negative terminal of digital ammeter, and the positive terminal is connected to the positive terminal of the digital ammeter. Okay. And then you need to close the circuit between point F and between point T. Similarly, you need to close the circuit between the points S and G. Okay. And the voltmeter. Okay, now in your setup there is only one voltmeter, so we need to use this particular voltmeter to measure the input voltage as well as output voltage. So what we can do is, since initially we will be doing input characteristics, so for input characteristics we have to first set the output voltage to a particular value, right? So to set the output voltage, what we will do, we will first connect the voltmeter onto the output side. So positive terminal of VCE is connected to positive terminal of voltmeter. Okay, and the negative terminal is directly connected to the negative terminal of the power supply. Okay, so first let us turn on the power supply. and we will set the output voltage to a particular value. Okay, you have fine and coarse adjustments over here. Let us say we'll set the output voltage to 1 volts. Okay, so once the output voltage VCE is set to 1 volts, you can change the voltmeter position onto the input side. Okay, so that can be simply done by removing this terminal of the voltmeter, and we will connect it to the input side. So input side, here is the voltmeter. Okay, done. Now what we will do, we will gradually increase the input voltage VBE in steps, and let us note down the input current IB. So IB, that you can see, right, this is your input current and this is your input voltage. So input characteristics is a curve plotted against VBE versus IB. So for the variation in base to emitter voltage, what are the variations in base current? So that gives the input characteristics. Okay, let's do that. So let us start increasing the voltage. Okay, so initial reading for 0 volt, 0 current. Okay, so this should be the, so for 0.2 volt current is still 0, 0.3 also it is 0, 0.4 0, 0.6 it is 0, so 0.4 volt it is still 0 amperes, 0.5, now you can see that the transistor is slowly getting into conduction. So for 0.5 volts you can write the base current as 1 amperes. Again for 0.5 now it is 3 microamperes, 0.5 7 microamperes. It is increasing, but the voltage is barely increasing, but the current is increasing significantly, you can say. Again for 0.5 it is 9 microamperes, for 0.5 13 microamperes, for 0.6 16 microamperes, 18 microamperes, 22 microamperes, 26 microamperes, 28, 32, 36, 40, 45, 48, okay, 49 microamperes, 54 microamperes. So basically what is happening, the voltage is staying constant at 0.6 volt and the current is increasing. Okay, so when you plot the characteristic curve, you will get a plot of this kind. You will get a plot of this kind. So this is IB versus VBE. Okay, so you are going on varying VBE and you are noting down the IB value, and this is the typical graph shape. Okay, initially the zero current flows and then gradually the current starts to increase in an exponential manner. Okay, so this is the exponential region, and once the voltage is at 0.6 volt level, okay, the junction basically breaks down. So basically if you drop a line, okay, onto the x-axis, you will get the breakover point over here. So for this particular transistor, breakover point is at 0.6 volt. So that is your input characteristics. So now what we will do, now we will set the output voltage to a different value, and for this new value of output voltage, let us redo the characteristics. Okay, so I'll reduce the input voltage to 0, and I will shift the voltmeter position. Okay. So initially we had set VCE is equal to 1 volt. Now we will set it to, let's say, 2 volts. Okay, so that's 2 volts, and we will keep it back, the voltmeter terminal. Okay, now once again you can redo the experiment. You start to increase the base emitter voltage and observe the microammeter reading simultaneously. For 0 volt, 0 current, 0 current. For 0.1 volt, it is 0 microamperes. 0.3, 0 micro. 0.5, it is 0 micro. Now you can see it has started picking up the current reading. So at 0.5 volt it is 5 microamperes, 6 microamperes, 9 microamperes, 11 microamperes. So basically you have to write for 0.5, 6 microamperes, 7 microamperes, 11 microamperes. Once again I will increase. For 0.6 it is now 15 microamperes, 22 microamperes, 27 microamperes. So what is happening is voltage is fairly remaining constant, but current is increasing sharply. That means to say, now the transistor has entered the linear region. So the transistor is behaving like a conductor, and the current Vi characteristics becomes almost linear. Okay, you can see 0.649, 0.648, 0.654, 59, 65, 68. Okay, now it has gone into 0.7. So at 0.7 it is about 73 microamperes, 0.7 80 microamperes, 0.7 85 microamperes, 92 microamperes, etc. So you can stop it somewhere over here. 0.7 it is about 92 microamperes. In the previous case you had got somewhere about 0.6. Okay, so that's your input characteristic. So what you can do, once you have these readings, you can plot IB versus VB. Okay, so I will tell you how exactly you will draw that particular characteristics. Okay, so after this video I will teach you about how to plot the characteristics of transistor. Okay, now let us look into the transistor output characteristics. Okay, so graph B basically talks about the transistor output characteristics. So transistor output characteristics is drawn by taking output current along y-axis and output voltage along x-axis. So basically it's a graph of IC versus VCE variation. Okay, for different values of input current. So what we will do, we will fix the input current at a particular value, let's say 20 microamperes, and then we will go on varying the collector to emitter voltage. Okay, And for this voltage variation, let us note down the collector current variation. So that is your first iteration. And for the second iteration, what we will do is we will change the input current to a different value, let's say 40 microamperes, and then redo the procedure. So as you can see, that the input current IB is set to 20 microamperes. Okay, for this particular set input current, let us note down the variation of IC versus VCE. All right. So let's start varying VCE. So this is VCE, and this central ammeter gives IC. Okay. So 0 0. So 0.1 volts, it is 1 milliampere. You have to be very careful because the transistor quickly gets into the saturation region. Okay, so you have to be very gentle with this fine voltage variation knob. Okay, so this is the fine voltage variation knob. Okay. So again 0.1. So 2 milliamperes. So 0.2 volts. Okay, 0.2 volts. So 0.1 volt, 1 milliampere. 0.2 volt, 2 milliampere. Okay, so 0.4 volt, 3 milliampere. Okay, you can see 0.4 volt, 3 milliampere. 0.5, okay, 0.6 volt, it is at 3 milliampere. 0.7, 3 milliampere. 0.8, 3 milliampere. 0.9, 3 milliampere. 1 volt, 3 milliampere. So that means to say the transistor output current IC is saturated at 3 milliampere value. So what are the readings? 0 volt, 0 current. 0.1 volt, 1 milli. 0.2 volt, 2 milli. 0.3 volt, 3 milli. And at 0.4 volt, 3 milliampere. But at 0.5 volt, the current started to remain at 3 milliamperes. Okay, so 0.5 volt, 0.6 volt, 0.7 volt, it was at 3 milliamperes. So this is your first set of output characteristics. Okay, yeah. Now what we will do, again we will reduce the output voltage to 0. Okay, and increase the base current to a different value. Let us keep 2 times the previous value, that is at 40 microamperes. Yeah, that's fine. 42, roughly 40 microamperes. Okay. Now let us redo the experiment. Okay. 0 volt, it is showing some garbage value. That's okay. Okay. So 0.1, 4 milliampere. You can see that the current is significantly larger, right? In the previous case, when your base current was 20 microamperes, for 0.1 collector to emitter voltage, you had 1 milliamperes. Now the base current is increased to 40 microamperes. So it is obvious that when the base current is increased, collector current should also increase, because collector current is beta times the base current. So if base current increases, collector current increases. That's the reason at 0.1 volt itself you have got 4 milliamperes. Okay, at 0.2 now it is 5 milliamperes. At point 3, 6 milliamperes. Point 4, 6 milliamperes. Point 5, 6 milliamperes. Point 6, 6 milli. Point 7, again 6 milli. That means to say the transistor output current IC is saturated to 3 milliamperes. In the previous case, it was saturated at 3. Sorry, for the present case, it is saturated at 6 milliamperes. So this concludes this particular experiment. Okay. So the plotting of graph I will teach you in the theory session. All right. All right. So this is the typical graph what you will get basically. So this is your input characteristics, okay, and this is your output characteristics. As you can see, initially there will be linear rise in collector current, and then the collector current gets saturated to some value. All right. So we will meet in the theory class. Thank you. Okay, these are the readings for input characteristics and output characteristics. So these readings have been picked from the experiment which was conducted earlier. All right. So the input characteristics were taken for two output voltages. VC is equal to 1 volt and VC is equal to 2 volts. Okay. Similarly, you can see the output characteristics. So output characteristics were taken for two input current settings. One was taken at IB is equal to 20 microamperes and the second one was taken for IB is equal to 40 microamperes. Okay. So what I have done is I have taken these values, okay, and I have plotted the graph. Okay, so the first graph is for input characteristics. As you can see that the input characteristics have been drawn for two sets of output voltage. One is VC equal to 1 volt and the second one is for 2 volts. Okay. Now while plotting the graph, quite often what happens is that you will get several points which may not be agreeing with the graph shape. So what you can do, you can kind of apply the curve fitting way. Okay, so the best possible points can be considered while joining or while constructing the graph. Okay, so that's for your input characteristics. Let me describe the scale. So along y-axis I have projected IB and I have taken 1 centimeter as 10 microamperes. All right, and along x-axis, okay, I have projected, you can see it is VBE and 1 centimeter is taken as 0.1 volts. Okay, similarly for the output characteristics, along x-axis we have voltage scale VC and along y-axis we have current scale IC. Okay, so 1 centimeter is 1 milliampere for y-axis and for x-axis 1 centimeter is equal to 0.1 volts. Okay, so once you draw the characteristics, what you have to do is you have to find out the H parameters from the input and output characteristics. All right, so first of all let me write down the H parameters. So firstly we have HIE. Okay, why HIE? That's because we are considering common emitter configuration. So HIE, okay, is equal to, basically the unit is resistance, hence it is small change in the input voltage. Okay, what is the input voltage? VBE to the corresponding change in the input current. So it is delta VBE divided by IB. Okay, so that's your HIE. And then you can find out HRE. Okay, so HRE is basically the reverse voltage gain. So that is the ratio of input voltage to the ratio of to the output voltage. So that is delta VB by delta VCA. Okay. And next we have the current gain, HFE. So HFE is the forward current gain, that is ratio of output current delta IC to the input current. Okay, so that's your HFE. And then finally we have HOE, which is basically the admittance, so which is the ratio of output current to the output voltage, VCA. Okay, so this is what we are supposed to find out. Now what you do is, let us identify delta VB and delta IB from the input graph. So what you can do, you can select a small delta VBE and delta IB in the transistor characteristics. Now there are two curves, you can select any one. Okay, so I'll select VC is equal to 1 volt because this graph is consisting of many points, so I may get an accurate answer. That's the reason. Okay, so what I will do at the knee, so this is called as knee of the graph. So you are supposed to take the data points at the knee of the graph. Okay, so somewhere over here I will construct my triangle. Okay, so the y distance is going to be delta IB. Okay, and the x distance going to be delta VBE. Okay, so delta IB is about 6 divisions. Okay, so it is 6 divisions, okay, or 0.6 centimeter into the scale value, that is 10 micro. All right, and in the numerator you will have to write on delta VBE. So delta VBE is about 1, 3. Okay, so it is about 3 divisions into the scale value. So scale value is 0.1. Okay, so I will get the HIE value. Okay, so here it is, 0.6 into 10 micro in the denominator and 0.3 into 0.1 volt in the numerator. Okay, so let us calculate. So that is basically so that's about 5000 ohms. Okay, so you will get HIE is equal to 5 kilo ohm, slightly large. Ideally it should be in the region 2 kilo ohm, 5 kilo ohm. That's okay, experimental result. Okay, your ambient temperature, everything it matters, the power supplies, fluctuations, etc. Okay, fine. So that's about the input characteristics. Now in order to find HRE, you need to have the value of delta VC, right? And for HFE you need to have the value of output current. So what we have to do is, now we have to go to the output characteristics. Now in the output characteristics, once again we will have to select the knee of the curve. Okay, so somewhere in this region we can select, this is your knee of the curve. Okay, somewhere here I will select. Okay, so this is my delta VC. Okay, and this is going to be the delta IC. Okay, delta IC. So we can proceed. Okay, so let me write down over here delta VCE is equal to, it's about 1 centimeter, so it is 0.1 volt, and delta IC is slightly above 0.6, it is about 0.7 milliamperes. All right, so your y-axis scale is 1 centimeter is equal to 1 milliampere. So here you have 7 divisions, hence it is 0.7 milliamperes. Okay. All right, so let me fold this graph. Okay, so let's calculate HRE. So HRE is delta VBE. So delta VBE, we already have the value. So it is 0.3 into 0.1, okay, divided by delta VCE. Okay, so delta VCE is again 0.1. Okay, so 0.1 gets cancelled. So you will get, okay, let me write it here. HRE is equal to 0.3. Once again, slightly bigger value it is. Okay, that it's okay. It is an experiment basically. Okay, again external factors matters. Fine. Next we have HFE. HFE is delta IC by delta IB. So delta IC we have found it is 0.7 milli divided by delta IB, that is 0.6 micro. Okay, so it is basically milli by micro ratio. Okay, so 0.6 division, so delta IB is 0.6 division into 10 micro, so that will give you the HFE value as 116, which is correct, 116. So here and there you may have some deviations, that's fine. Then finally the admittance HOE. So HOE is delta IC is 0.7 milli divided by delta VCE. So delta VCE is 0.1 volt. So it is 0.7. Okay, that is HOE is equal to 7 10 to the power minus 3 mho or Simon. Okay, so finally you can write down the H parameters of common emitter configuration. Firstly we have HIE, which is 5 kilo ohm. Then we have HRE. Okay, so HRE is 0.3, it is dimensionless. And then we have HFE, which is 116. And then finally we have the admittance HOE. Okay, that is 7 milli. So 7 into 10 to the power minus 3 Siemens. Okay, so this is the experiment. Now what we have to do is you have to use the conversion equations to calculate the H parameters of common base and common collector configurations. Let me tell you how exactly you do it. First let me write for common base CB configuration. So CB configuration, we have first of all HIB. So HIB is HIE divided by 1 plus HFE. Okay, so that is equal to HIE is 5 kilo ohm divided by 1 plus HFE. HFE we obtained as 116. So that is 42.73 ohms. So that is your HIB. Okay. Then we have HRB, the reverse voltage ratio. So approximately the HRB is given as HIE into HOE divided by 1 plus HFE. Okay, so HIE is 5 into 10 to the power 3 into HOE. Okay, so HOE is 7 milli divided by 1 plus HFE, so 1 plus 116. So HRB is 0.299. Okay. Then we have HFB. So HFB is minus HFE divided by 1 plus HFE. So that is minus 116 divided by 1 plus 116. So basically it is 116 divided by 117. So very close to unity as expected. So it's about 0.99. Okay, negative sign. And then finally we have HOB. So HOB is HOE divided by 1 plus HFE. So HOE is 7 milli divided by 1 plus 116. So that's 5.98 into 10 to the power minus 5 Simon. Okay, so one mistake I have done, no, that's correct. So this is your common base configuration. Okay, then finally we have common collector configuration, CC. Okay, so common collector configuration, HIC, sorry. So HIC is approximately equal to HIE, so that is 5 kilo ohm, and HRC is 1 minus HRE, approximate expression, so it is 1 minus HRE is 0.3, so that's 0.7, and then we have HFC. So HFC is negative 1 plus HFE, so it is 117, and then finally we have HOC. So HOC is approximately equal to HOE, and that is 7 milli. Okay, Siemens. All right, so this is your determination of transistor H parameters using the transistor characteristics. Okay, so quickly to sum up, what we did was we conducted an experiment on common emitter configuration, and from that experiment we determined the common emitter H parameters, namely HIE, HRE, HFE and HOE. So by using the H parameters of common emitter configuration, we found the H parameters of common base and common collector configurations. Okay, so for finding out the H parameters of CB and CC, what we did was we used the approximate conversion equations. Okay, so these approximate conversion equations you need to remember. All right, so that's the end of experiment number 2 from analog electronic circuits. Thank you.